Log on, tune in, find out. Another good idea from Cambridge.
Of this afternoon session, and our first speaker will be Sheehan Olver from Oxford, and he's speaking on the numerical solution of Riemann-Hilbert problems, and he's applying that to the Painlevé II equations.
Thank you. So I guess in the Hop program, were quite a big theme, and I'm going to demonstrate that. So they're used a lot for analysis, and I'm going to demonstrate that they can also be used as a numerical tool. So, well, we'll begin with a description of what a Riemann-Hilbert problem is, and then we will see that the key is that they can be reduced to a linear problem using the Cauchy transform. And so then the key is computation of the Cauchy transform. Oh, sorry, I forgot to turn it on. Okay. So then using the computation of a Cauchy transform, we can then construct a spectral method which will enable us to solve the Riemann-Hilbert problem. All right, and then I'll apply it to computing solutions to Painlevé II. And then this can be extended for large values of x, so in the asymptotic regime, but converging to machine precision and accuracy using the method of nonlinear steepest descent. Okay. So Painlevé transcendents are classical objects, so they're nonlinear ordinary differential equations such that all the movable singularities, so singularities that depend on the initial conditions, are poles. And so they have many applications in sort of integrable systems theory and other areas like random matrices and orthogonal polynomials, and then many physical applications as well. And they're sort of come to be viewed as nonlinear analogs to the linear spectral functions that we're all familiar with. Okay. So now the question might be what's so hard about them that makes them difficult to compute? So let's look at probably the most important solution to Painlevé II, which is the Hastings-McLeod solution, which is used in random matrix theory distributions. And so it looks very smooth, and we have initial conditions in terms of the Airy function, and it solves a fairly straightforward ODE. So it looks like we can just integrate it using any numerical integrator. But then the problem is, as soon as we perturb the initial conditions, which we must in numerics, two possibilities occur. So if we perturb it above, it behaves like the Airy function. So we have oscillations. If we perturb it below, we then have poles, and infinitely many poles. And no matter how much we improve the initial condition, it'll only push the oscillations or the poles further out. So using a time-stepping method, it's not possible to compute the Hastings-McLeod solution. And then another aspect is, in general, solutions to Painlevé II have poles, but using the approach that I'm going to develop, we can integrate past the pole. So we can evaluate past the pole, and that's how I generated these plots. Okay. So the key is, instead of using the differential equation formulation, we can reformulate the Painlevé II transcendent as a Riemann-Hilbert problem. Okay, so what is a Riemann-Hilbert problem? So we're given some curve, let's say gamma in the complex plane, and we're given a function g, which happens to be matrix valued along this curve. And we want to find a function phi which is analytic everywhere except on the curve itself, so it has a branch cut on the curve, but it has limits from the left, so phi plus, and limits from the right. And we want this function phi to have this jump relation. So we want the limit from the left to equal the limit of the right times our given function g. Okay. And just as Painlevé transcendents are sort of nonlinear analogs of special functions, these are sort of nonlinear analogs of integral representations. And so they've been used to sort of determine asymptotics similar to how integral representations are used to determine asymptotics in linear special function theory. And the key is that they can be deformed in the complex plane. But until this method was developed, there hasn't really been an effective numerical way of computing them. So I'm going to show that they can also be used, sort of how integrals can be used for quadrature. Riemann-Hilbert problems can be used in a numerical capacity as well. All right, I'll gloss over the slide, but basically other integrable systems, KdV, nonlinear Schrodinger, can also be written as Riemann-Hilbert problems. And just briefly, where these come from is we start with a nonlinear differential equation. Somehow we get a lax pair. Then we can analyze this linear coupled differential equations to find the monodromy in Stokes zeta. But then that uniquely defines a solution. And so we can actually take this process back up the chain to get a solution to the differential equation. Okay. So in the case that I'm going to be focusing on, Painlevé II, this will be the Riemann-Hilbert problem. So instead of specifying initial conditions, we'll have Stokes multipliers. So three constants, S1, S2, S3, which satisfy this relationship. And so they form a two-dimensional manifold. Okay? And so we choose these. Those are sort of like initial conditions. They define our solution. And then this is our jump curve. It consists of 6 rays, and that's the origin. And so the valuation of u is here. There's the x there, so that x becomes a parameter. Z is the variable in this plane, and it has the form of an exponential along each of these 6 rays. Okay, and so if we solve this Riemann-Hilbert problem to determine a function phi, we can then recover the original function u by just taking the limit as z goes to infinity of the 1-2 entry of the matrix. Okay. So our first task is, right now we have the problem of finding an analytic function, and we're given a function on a curve. So our first task is to reduce it to only finding a function on the same curve gamma. So, well, first, wait, I got ahead of myself. So first, we want this to go to the identity matrix at infinity, but we want to make it so it goes to 0. Therefore, we have superposition. So we just replace phi with psi plus identity. So if psi goes to 0, phi goes to the identity. And therefore, we get this linear equation with the condition at infinity that it goes to 0. Therefore, we can add solutions, and we have superposition. Okay. Now, consider the Cauchy transform. So the Cauchy transform over our curve gamma is defined as this. And what it does is it takes a function defined on gamma and extends it to an analytic function everywhere off gamma. And so if we just pre-multiply our map before, for some curve v defined on gamma, this gets extended to an analytic function everywhere off gamma. So if we solve this equation, the Cauchy transform of v then solves the original Riemann-Hilbert problem. All right. And the key is, rather than looking at this as an integral transform, we'll look at it as having the property. This is due to Plemige's lemma that the limit of the left of the Cauchy transform minus the limit on the right equals f. So here we would have to deal with some sort of singularity. And essentially, if we were to use quadrature, we'd be approximating a function with a branch cut with rational functions, which won't be accurate near the branch cut itself. But if instead we look here, everything's analytic. So f is analytic, and the Cauchy transform, or well, f is, say, smooth on gamma. The Cauchy transform is analytic, so we don't have to deal with singularities at all. Okay. So let's say that we can compute the Cauchy transform accurately. And so we can then also compute the operator here. And then we can just solve our equation as a collocation system. So we're given some points on the curve gamma, x1 to xm, some basis, and we just solve this linear system. And that gives an approximation to the function v. and the Cauchy transform of that approximation is then approximately the solution of the Riemann-Hilbert problem. Okay. So we've reduced basically everything to the problem of computing the Cauchy transform. So we want to compute the Cauchy transform over a domain, this 6-star domain. It's an integral transform, so we can decompose it into its individual parts. And so we're left with the problem of only computing the Cauchy transform over a single ray. Cauchy transforms, if you have a conformal map from one domain to another, you can find the Cauchy transform as well. So we can conformally map these rays to the unit interval. And so we've reduced everything to the question of computing the Cauchy transform on the unit interval, as well as its left and right limits. But Z has to be complex, or can be complex. Okay. So I'll start with the case of how, let's say instead of a unit interval, we had a circle. How could we compute the Cauchy transform? So we're going to use the definition that the limit from the left minus the limit from the right equals some function g, and then we want it to vanish at infinity. And so we assume g is smooth. It has a representation as a Laurent series, and the answer is fairly straightforward. We take all the positive terms in the Laurent series, put it inside the circle. That's an analytic function in the inside the circle. Take all the negative terms in the series, put it outside the circle. This minus that, the minuses cancel, returns our function g. So this is an efficient way of computing the Cauchy transform over a circle. And of course, in practice, we just do this with FFT, because all we need is the Laurent coefficients. So. Okay. So now we want to take this idea of solving the Cauchy transform on the circle and use it to solve it on an interval. Okay. And wait, actually I'm going to skip this slide. Sorry. Okay. And the natural map, the natural conformal map from the unit circle to the unit interval is the Joukowsky map. So it's just half z plus 1 over z. It maps the interior and the exterior of the circle onto the slit plane. Okay. And then we have four inverses. One maps the slit plane to the interior of the circle, the other to the exterior. And since we want to evaluate on the branch cut itself, we need reliable maps on the branch cut. So we have two more maps, one to the upper half circle for values on the interval and one to the lower half circle for values on the interval as well. And then we have a simple relationship. The map to the interior of the circle from the bottom goes to the upper half circle, from the top goes to the lower half circle, and so we have these relationships here, and then it's sort of the opposite if we map to the exterior. Okay. So now let's say we solve this problem. We want to find the Cauchy transform, and we map f from the interval to the bottom of the circle, and then minus f to the top circle. So let's say we can solve this problem and compute the Cauchy transform of such a function. So we get a phi plus and a phi minus, and then we just define the Cauchy transform of f over the unit interval as we take the contribution from the interior and add the contribution to the exterior. And then we can see that this is indeed the Cauchy transform by taking the limit from above. The plus goes to a down arrow, the minus goes to an up arrow, and from below it's the opposite. But this minus this is f of t of z, because that's the relationship here. And then this minus this is, or phi plus up arrow minus phi minus up arrow is minus f of t of z. The minuses cancel, and we get back f of z. And we also get that it decays at an infinity. So this is indeed the Cauchy transform over the unit interval. Okay, so we've reduced it now to the problem of of computing the Cauchy transform over a circle. But the problem now is that we have a jump at plus or minus 1. So we can't just use a FFT Laurent series. All right. But so instead of expanding f in a Laurent series, we're going to subtract out the sign argz, so this jump. And so we can officially represent f minus f in this series. So this takes into our, this is plus 1 below the circle and minus 1 in the upper half circle. Okay, and so we can efficiently represent this function in terms of this series. And so if we can compute the Cauchy transform of this, we can then compute the Cauchy transform of that efficiently. All right, and for the first moment, the answer is fairly straightforward to arrive at, which is just arctang z in the interior of the circle, arctang 1 over z. And if you look at these figures, you can see that this minus that, we get back the sine function, and then we get something else when we add that. Okay. So now if we just multiply that function by z, we get the correct jump relationship, but we don't get the correct condition at infinity. But the solution is we know the, so at infinity it goes to 1, and we want it to go to 0. But we can just subtract out 1, so now this goes to 0 at infinity, and then we just add it back here, and now this subtraction cancels, and so this is the Cauchy transform of z sine argz. And so you can then get all of the moments by just looking at the Taylor series of the arctang function. Fortunately, it satisfies a very, very simple recurrence relation, and therefore we can efficiently compute these moments without any problem. So I'll just take it as given that we can compute the Cauchy transform for the Chebyshev basis on the unit interval uniformly in the complex plane, including on the interval itself, the two limits on the interval itself. And we also know precisely the asymptotic, so it blows up at plus or minus 1, but we know precisely the asymptotic behavior, and this will be key. Okay. So just briefly, we can then use this to find the Cauchy transform over the half line. We just apply this conformal map. If you look at this, it'll obviously vanish at infinity, and it'll also satisfy the jump relationship over this. So therefore, we can map it to the unit interval and find the Cauchy transform over each of our rays without any problems. Okay. So now we want to construct our collocation system. And what's key, and so another way of viewing this problem is as a singular integral equation, which people have done in the past. But the problem is then you end up having to have exponentially many points near the singularity, so near the endpoint. So it's not very efficient. But the key is, because we know precisely the asymptotic behavior at the endpoints, we can include the endpoints themselves in our collocation system. And this way we don't need the exponential clustering at the endpoints. Okay. So we have this expression for the Cauchy transform over each of our rays in the complex plane. And then we can rewrite this as this term, just expand logarithm by its definition. So we have this term which will blow up, but this term which is bounded. Now, if you notice, this is f naught, so it's the limit on gamma k. So let's say we sum over these functions, v1 up to v6. These terms will add up here, plus these bounded terms. But then if we're fortunate enough, which the true solution must satisfy, that this terms, the limit along each ray of what we're approximating sums to 0, then this is automatically bounded. The logarithmic term vanishes. Okay. So what we're going to end up doing is just throwing out the logarithmic term, ignoring it completely, and defining the Cauchy transform as 0 as the bounded part. Okay. So now, using this definition for our collocation point at 0, we can construct our collocation system, and then we just use the map Chebyshev points for the other points, and each of these values are computable, and there's no problem. We can construct the spectral system, we can solve the linear system. In practice, it's only badly conditioned. It appears to only be badly conditioned if the Riemann-Hilbert problem itself is badly conditioned, so it's perfectly fine. Okay. Now, if we assume this sort of additional condition, which is almost always satisfied, then our act of throwing away the logarithmic term causes the approximate solution. Just this co-location system itself causes all the contributions to sum to zero, so the logarithmic term is automatically canceled, and therefore our definition of the Cauchy transform at zero is the correct definition. And then if this isn't satisfied, we just add an additional condition saying that they have to sum to zero, and that's not a problem at all. Okay. So now we use this method, we get an approximate solution to the Cauchy transform. What we want is a limit as z goes to infinity, but this z goes into the Cauchy transform, it cancels out, and it's left with just the problem of integrating our basis over the rays, which is a solved problem. We know that in closed form because we're representing everything as Chebyshev polynomials. Okay. Or maybe not closed form, sorry, but we can efficiently compute it. Okay, and we can also find the derivative, and so this appears to be the first reliable map from Stokes data, which is probably what's the physically significant thing in Painlevé transcendence to initial conditions. Okay. So we're going to return to the Hastings-McCoy solution. Fortunately, we have numerical values online, so like I said before, it's very hard to integrate it, but I think what they did was they used very, very high precision arithmetic and Taylor series methods, and that way they were able to get accurate data values. So obviously, if you take enough precision, it'll push the singularities and the oscillations far enough away so that it's accurate in a given region, but it's a very inefficient method. Okay. So now we apply my approach with different values of points, and what we see is clear spectral convergence. So this is the error, and but obviously the solution itself is badly conditioned because we saw that the perturbations in the initial condition cause poles or oscillations, and that's going to be true for perturbations in Stokes data as well. And so you see exponentially bad conditioning as we go to minus infinity. And actually, if we look at the relative error, we see it in both directions. Oh, but I should mention that it's in this regime, so x close to zero, the better approach is Folkmar's Fredholm determinant approach. But that will not be accurate in the tails, so as x goes to, x becomes large. Okay. So here's some other plots of other solutions showing sort of how exotic Painlevé equations can be. So here we have something that behaves almost exactly like the Airy function. Here we have another example with infinitely many poles. And here we have this very stiff behavior. Okay. So now we're going to be interested in the asymptotic regime, so x becoming large, because the existing approach breaks down. It only works well for x close to zero. And the key is this becomes oscillatory as x becomes large. And it also becomes increasingly stiff along the imaginary axis. Okay, and both of these issues can be resolved by deforming the contour using nonlinear steepest descent. I guess I don't have too much more time, so I'll gloss over this. But anyways, so just like standard steepest descent, we begin with deforming through the turning points. So along each of these rays, we've turned the exponential, or the oscillations into exponential decay, but we still have this connecting ray to resolve. Fortunately, we can split, if we have this jump curve, these are matrices A, B, C. We can split it by putting C above, B in the middle, and A below. And fortunately, the LDU decomposition factorization satisfies that will exponentially decay in each of those regions, so we can use that. And then we get this Riemann-Hilbert problem. Okay, and then unfortunately, the solution will oscillate on that connecting ray, so we have to get rid of it. So we use a parametrics, but so then we define this function phi, and then we end up with this Riemann-Hilbert problem. Okay, but anyways, we can then implement all of the oscillations that become exponential decay. That's sort of the key message, is we can deform the contour and it becomes exponentially decay, and we can apply this approach, and we can do it for positive values as well. So we can extend this graph using these two approaches, one for positive, and we get this, so we get the accurate representation of this very stiff behavior. And there's no reason we can have to stop there. We can have x equal to 1,000 as well, and it seems believable. And we also get accuracy for Hastings-McLeod. So I think the conclusion is that using Riemann-Hilbert problems, we can accurately compute these nonlinear differential equations, as long as we use a properly formatted Riemann-Hilbert problem, which happens to be the one that's deformed along the path of steepest descent. All right. And we can apply this to other Painlevé equations. Here's a picture of Painlevé IV. We can also apply it here. Here are some distributions in random matrix theory. And there's a Mathematica package available online with all of this implemented in it. Thank you.
Are there any questions?
Yes. I think this is a very important application in the theory of Riemann-Hilbert problems. You noted that when the Riemann-Hilbert problem has a solution, then your collocation system has a solution. But then you saw some solutions which had poles, so probably there something must break down. What do you do in this case? When your system, so when the Riemann-Hilbert problem doesn't have a solution, it must be that your collocation system breaks down.
It becomes badly conditioned.
What do you do then?
Well,
how do you cope with those situations?
well, I don't think it has relative accuracy near, or I don't think it is accurate in the poles. So what happens is that the spectral system becomes badly conditioned.
And then what do you do? I mean, you saw some graphs though where you seem to show that you could deal with the pole somehow.
Well, it only becomes very badly conditioned very close to the pole. So
Ignore those points. Is that what you do?
well, if you're never exactly on a pole. So
you stay close and then you.
well, there's no such thing. With probability 0, you're never at a pole.
Okay, thank you.
Or probability 1.
Yeah. First questions?
Actually, I have a few questions. First of all, the Painlevé equation is a Hamiltonian equation. Have you somehow preserved this Hamiltonian structure throughout the process that you're doing?
Not that I know of.
Okay, and second question is there also the discretization, integrable discretization of the Painlevé equations, including Painlevé II. So do you know? Have you?
What do you mean integral?
Integrable.
Discrete. Yeah, I'm not sure.
Okay. Yeah, that's a good point. I see. So you mean if you could use this discrete to solve it numerically, you mean instead?
Well, some comparison.
Oh, you mean the discrete Painlevé II equations? I'm not sure if there is a connection. I'm not sure how much is known about the relationship between the continuous Painlevé II and the discrete Painlevé II, but
Well, there's a fair amount now. But, and then I guess my final question is So here you've done this very nice work, using the relationship between a nonlinear ODE, integral ODE, and a linear integral equation. Now, similar things, quite similar things exist for integral PDEs, such as the KdV equation.
Yeah.
Painlevé II is a reduction. So, could you do similar things for the KdV equation?
Well, the challenge with the KdV is so for a given analytic initial condition, it would probably be fairly straightforward to do similar things, and I have applied it to the sort of small x, small t regime, and it works. The problem is, if you wanted it for a general numerical routine, you first have to compute the reflection coefficient, and then that's not good. You're not going to know anything about its behavior in the complex plane, so you wouldn't be able to do a deformation. So you'd have to use some other way of handling the oscillations without deforming in the complex plane for general initial conditions. I'm hopeful there is it's possible, but I don't know.
I see you're saying that they say for Painlevé you can do it complex, but for the KdV you're interested in real.
Well, for Painlevé, I know everything about the jump curve. I know where. Well, I know its entire. I know where I can deform it. I have all that information, that analytical information. But here, and so here, if you give me the reflection coefficient, I can also solve this Riemann-Hilbert problem on the real line. That's not a problem. And in fact, it's a lot simpler than what I showed because it ends up being a Teplitz matrix. But the problem is this reflection coefficient R, in general, I don't know what it does in the complex plane. It might not even be analytic at all. So
No, it's not. It may. It's not in general.
yeah. Well, it might be, but
No, but for very, very limited class of initial conditions, they have to be exponentially decaying.
yeah.
But for general initial conditions, you do not.
Right. Yeah, exactly. So, but then so even though I know this oscillator, I know its path with steepest descent, I can't actually use that information because I don't know R in the complex plane. So there might be, I mean, this is similar to like computing oscillatory integrals where you can actually compute them without deforming in the complex plane, but I'm not sure how those ideas apply to problems such as this. So.
Just make one quick remark. See, as you know, that and Zhu for this problem they did two things. One is at the beginning they did this rational approximation, which is not very effective. But then recently they have an alternative way, which avoids this rational approximation. And this alternative way is complicated, but this could be then more useful for you because then I think such a deformation might be possible. So my suggestion is that to follow their more recent work, and maybe this.
Who's?
I'll tell you what the reference is.
I think you both should discuss this point further in the break. Thanks, Sheehan, again for this.